topics are relatively short. The first one, part C, role of data structures in algorithms. And sometimes we need to consider to choose the right data structures. In Module 1, I like to use a simple example to show you the importance of data structures. All right, C.1, search unordered arrays. So this is a simple problem. Our computing problem, number 3, search an unordered array. The question, given an unordered array, we use this representation. The data size is n. Okay, and a search key k. Search key. Here, the search key you can understand in this way. So the key value should be one of the values in the array elements. Should match one, not that, should, could, because there is a possibility there is no match. Later we will have that case. Not should, could match one of the elements in the array. All right. Now, our goal to find an index I such that k equals A of I. There is a possibility this I cannot be found. That case could happen. So, all right. So this question, very simple. I believe everyone in this class, you can solve this easily. Search. You just compare the search key k with all the elements. So you run a for loop from beginning to end, compare one after another. When you find a match, you get out of the for loop, right? So that's basically what you need to do. But here we like to consider a few basic concepts in this simple question. First, the problem type, basic problem type. We have several basic problem types in this class. This gives us the first one in this type. So which type? Search type. Search type. And the data structure used here, array. Also, basic type, array. Later, we will learn some more advanced data structures. But most of the time, we use array data structure. All right. And here, I give you the reference in the textbook, section 2.1. All right. So the question, why the data structures are important in algorithm design. Here, I like to point out important usage of the data structures. Make our data well organized. That's the important way we use the data structures. Organize our data with some special properties. Yeah. We can choose organizing the data or do not organize the data. Yeah. We have options. If you like to organize your data, you need to pay some cost. You need to, pay some effort to organize the data. But after you organize the data, your data should have some desired properties so you can enjoy the good properties, the good results. Yeah. So later we have another example so I can show you, to pay some cost for preparation, for data preparation, you can get better results. You have a chance to get better results. Yeah. Data organization in our second example, if you recall the chessboard question, counting number of squares in the chessboard, we organize our data for different data sizes, right? 1 by 1, 2 by 2, different data sizes. That's a simple way to organize data. Yeah. Later, we will have many different ways to organize our data. Yeah. So here, I just, at a high level, pointed it out. To organize the data in the preparation step, it could be very useful. Okay? All right. Yeah. But for this question, actually, we do not pay any effort to organize our data. We just take the data given. Then we solve the problem immediately. We do not organize the data. Yeah. But all right. Through data structures, so that our algorithms can take advantage of the structures. Now, here I like to point it out a common way that people do to organize the data. So that is sorting. Sorting. Yeah. Given unordered data, so we do not arrange the data in ascending order, in any order. Yeah. But what do you mean to organize data? Here, I give you one commonly used method to organize data. So that is sorting. Sorting. Okay? You need to pay quite a bit cost. Yeah, because sorting is pretty expensive. Yeah. But after you pay that much cost on sorting, then you enjoy the result with the property data is ordered in ascending order. The data is organized in ascending order. Then your algorithm, when you design your algorithm, you can enjoy the ordered data property. How about that? Then your algorithm could run much faster on ordered data. So that is one typical way that people do in many of the computing problems. All right. Yeah. Yeah. But we will see that example later. Okay. Yeah. All right. So here, let's solve this problem quickly, because this is a very simple problem. Yeah. Basic operation comparison. Yeah. And when we do comparison, each step, we have several different results. equal, not equal, greater than, less than. Yeah. But when we do comparison, we start from the first element in the array with index I equals 0. Okay. So then in every iteration, we compare k with the current element, a of I. If they are equal, then we return index I, and we can terminate the program, because that's all we need to do. Yeah. But if k is not equal to a of I, then we need to move to the next iteration. Compare k and a of I plus 1 and repeat, But your program has to terminate at the end. And after you compare k with all the elements in the array, yeah, so that means your I moves to the last index n minus 1. After that, you do not have a match. Yeah. No match. Then you return -1. Yeah. So your function, the return of value -1, yeah, because it's not a valid index number. A valid index number cannot be negative. So you use -1 to tell, the programmer or user, there is no match. That's possible. Yeah. So this logic, using this simple logic, you complete the whole solution. Yeah. So that is the whole solution. Okay. Yeah. All right. So after that, we want to have some discussion. Yeah. So first, this algorithm, very simple, yeah, but there is a name for it. Yeah. One we call a sequential search, but also another name, commonly used name, linear search. So sequential search or linear search. Yeah. And it is a basic, our first search algorithm. Later, we will learn another important search algorithm, binary search. Okay, yeah. After that, we learn another advanced search algorithm. Yeah. So we won't have many different search algorithms. Yeah. But this is the first one. Yeah. All right. Here, this question, how do we measure its performance? We know its basic operation is comparison. In this question, we do not do addition, we do not do multiplication, as in our polynomial evaluation. So our basic operation is comparison. So how do we measure its performance? Naturally, you can see we use the number of comparisons. How many comparisons do we need to find the given key? Yeah. That's the measure, number of comparisons, that's the measure, okay? Yeah. But there is another question. Yeah. If you use the number of comparisons, then you have the chance, sometimes when you are very lucky, when you do the first comparison, you find your key to be searched in the first comparison. So when you are very lucky, okay? But many times you may not be that lucky. Yeah. So you need to do comparison with many elements in the array. And you have the chance, you need to compare your search key with all the elements in the array. So here you have the best case, you have the worst case. Okay? Yeah, right. Yeah. Oh, yeah, case one, yeah, best case and the worst case. Yeah. But when we talk about measuring the performance, which one, which case should we use? Should we use the best case or the worst case? Yeah, if you use the worst case, all right, so let's think about if you use the worst case. For this particular question, our worst case, we need to use n comparisons, right? Because we need to compare the search key with all the elements in the array. That's the worst case. Okay, so let's think about if you use the worst case, that means you give people impressions that we need to use n comparisons. Is it the best way to describe the search performance? Okay, do you think that's the best way to describe the search performance? Okay, yeah. All right, let me give you a little more background information so you can think about if this is the best way for the search performance. Give a range. Yeah, all right. So here we talk about the number of comparisons. Okay, yeah. So you want to have a range for the values, of the array elements, that range. You want to have that? Yeah. That, yeah, but if we look at the comparisons, that range may not have any impact, right? Think about that. Yeah. If the range is between 0 to 100 or 0 to 1,000, is there any difference? You still need to do the same number of comparisons, right? Yeah. Think about that. Yeah. All right. So here, let me go back to what is the fair measure for this algorithm? I want to address this question first. Yeah. The fair measure. All right. Let me give you a little more background because the search operation, think about everyone may do search operations every day, right? When you search, you type keyword in a search engine. That's the search operation. Okay, you type a keyword. Your keyword, that's the search key. Here, our K. Yeah. Although in this question, we use some number for K, but when you type a word, can we convert it to a number easily? Yes. If we like, we can convert any word to some integer value easily, right? Yeah. So it's not a big difference. Or we do not need to do conversion. We just compare a word with array elements, and we assume our array elements also take the string values, string array. Yeah, we can do that comparison also. Yeah. So think about that. So when you type a keyword in the search bar of a search engine, okay, then the search engine will, use that keyword so then to do the search in a pool of data. A pool of data, right? Yeah. Think about that, pool of data. Yeah. Here, our array, it's just a model of the pool of the data, right? Yeah. In the real world, that pool could be huge. a huge pool. Yeah. Yeah, but here we want to simplify that pool. So we use an array to model that big pool data. Okay. Then you have a chance, the first element in the array, you hit it, then only one comparison. After that, you may have 2 comparison cases. Then you have 3 comparison cases, and so on. And the last one, you have n comparison case. The question, which case do you feel is the best to describe the overall measure? This question, overall measure. Okay? Yeah, because sometimes you hit 1, sometimes you hit 10, sometimes you hit 100. There are so many people in the world do the search operations every day. Some people fall into, so yeah, here the range probably. Yeah, so here I got your, Jeanette and Madison. You talk. Oh yeah, Jeanette first. The range. Some people, the number comparison may fall in a range between 0 to 10. Some people, the number of comparison may fall into the range between 10 and 20, and so on. Okay, if you're thinking that way, so then you can talk about range. Yeah, but here, Madison gives a good answer, average. Average. Yeah, that's the best way to describe the overall performance. We need to take average. People do millions of search operations every day. Okay? Yeah. So the number comparisons are distributed from small number, then large number. Yeah. But at the end, you need to consider the average number of comparisons. So we call it average case efficiency. So we have the best case, we have the worst case. Yeah, but here we need to run this algorithm so many times, millions of times. So which measure is the closest description of the overall efficiency? The average case efficiency. Yeah. So you may ask how to define average case, right? For the best case, you can understand easily. For the worst case, you can also understand easily. But for the average case, you know how to take average of n numbers, right? When you have n numbers. Yeah. So here, let me write our first understanding of the average. When you have n numbers, 1 plus 2 plus 3 plus n. Yeah. This could be our first way to define the average, right? Yeah. This could be the most straightforward way we can use to describe the average number of comparisons, right? Yeah. But for this search problem here, if you use this expression, you ignore several important factors. You ignore several important factors. So you have to consider some important factors. Yeah, so in the next slide, we need to consider another important factor in order to represent this average number in an accurate way. This version is not that accurate. Most of the time, it's not that accurate. Yeah. So we have to consider a few more factors to get a much better, more accurate expression. Okay, all right. Yeah. So let's consider the, the operation we need to count the number of comparisons. We need to study all the possible cases. Then we can look at the average. We need to understand the details of all the cases first. So let's do a chart here. So let's list all the cases here, but you can see there is another important case, no match case, we also consider here. In the previous slide, when I write the average case formula, I didn't consider no match case, right? If you go back to look at that formula, we didn't factor in the no match case. You ignore that no match case. That's one of the reasons that version is not accurate. All right. So here we consider that no match case. A of 0, 1 comparison, A of 1, 2 comparisons, and so on. A of n minus 1, we need n comparisons. And for no match case, also n comparisons. So now, how to take the average? So here you can see we add, in our previous slide, we ignored the last case, no match case. Now, we get it back. After we get this no match case back, let's look at the average number of comparisons. Okay, Now, let me write one formula here, and you tell me if it is correct or not. Okay, because here we have n minus 1 cases, not n cases. Oh, sorry, n plus 1 cases. No match, so we add one more, n plus 1 cases. Now we should do average for these n plus 1 numbers, right? So let me write this formula. The space is a little small. 1 plus 2 plus ... plus n, the first n case, then the last case also n, divided by n plus 1. How about this expression? Tell me, is this a good average number for this algorithm after we factor in no match case in this way? Do you think this is an accurate average number of comparisons for the search algorithm? Think about this formula. It looks a little better than the previous one, but is there something missing here? Is there something missing here? Okay. Anything important not considered in this formula? Okay. Nobody answered. But actually there is another important factor not considered. Okay. Here, when you take average in this way, you assume each case occurs with the same probability, right? Case 1, case 2, and a no match case occurs with the same probability as any of the first n cases. That's usually not right? We cannot assume that. That assumption is incorrect most of the time in the real world applications. Okay, so here, the important factor we didn't consider, that is the probability for the no match case. We need that probability number. That number is important. So, but that data, people need to get that data in some way. People can use the history, history, statistics in history data to estimate that probability. But you need to find it first. Before you calculate the average number of comparisons, you need to find that probability number. Okay, yeah. So here we have best case, worst case. Yeah, but the worst case, you need to consider two subcases, right? Two subcases, both n number of comparisons, but they may have different probabilities. Yeah. All right. Yeah, so here, right? So we passed this step. We know we should use the, average case efficiency. But the question is how to represent the average case efficiency in an accurate way. That's the question we need to answer at this point. Yeah. So we need to make some assumptions, make some reasonable assumptions here. That probability, mainly regarding the probability for individual cases. Yeah. All right, so let's do that probability. Okay, assumption. Assume that for the first n cases, yeah. So our first assumption. Assume that these n cases have the same probability. That's okay. Yeah. Yeah. That's the, in general, we use that assumption in our real world applications for the first n cases. Okay. Yeah. Then we also need to make assumption for that no match case probability for the index case. So that's the matching case, right? Index. Yeah. So you can find a matching element, a matching array element. So matching case, the index case with probability P. So that means this P should be given at the beginning. Okay? Yeah. Yeah. How to get that from the history data? We do statistics from the history data. So we estimate that P. Okay? Yeah. After we get that P, that means with this P, little p percentage of chance, the given key K appears in this array. Okay? Then for the no match case, -1 case, its probability is 1 minus P. Okay. After these two assumptions, now we can write our average number of comparisons in an accurate way this time. Yeah. The best description we can find for the average case efficiency. Okay? Yeah. So let's do our final formula, final version of the average case formula. Okay. Yeah. All right. C.2, let's find the average efficiency formula. Yeah. All right. Okay, yeah. Here, we use the weighted average. This time we modify our, early versions of average. We will choose appropriate weights when we consider all the cases. The weights could be different. The weights not always the same. Yeah. So in our current question, the weights could be different. Yeah. So we consider the weighted average. And we use two-step calculation. Yeah, because we have matching case and a no match case. So two-step. For matching case, what is the average? For no match case, what is the average? Then we apply weighted average on these two cases to get a final average. Okay, so let's do the calculation in this way. Yeah. Subcase averages first and overall average second. Okay, yeah. All right, the first, yeah, so we can treat the first subcase, matching case. How about the matching subcase? Right, yeah, so we can find a valid index I for which k equals A of I, that subcase. Yeah. So the average for this subcase is easy, right? Straightforward. Yeah. Because each one, yeah, we in our first assumption, each of the n cases occur with the same probability, 1 over n probability. Okay, 1 over n. That's our assumption, first assumption. Yeah. So with this assumption, the average for this subcase, yeah, the matching subcase, so that is 1 plus 2 plus dot 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 n over n. After simplification, 1/2 times n plus 1. But that's for the matching subcase. This average number is for the matching subcase. All right? No match subcase, only one subcase, right? Only one to be considered. So that means its average also 1. Yeah. So that's easy, only 1. Okay? Yeah. But now, our last step, we need to consider an average between these two numbers. Another round of average between these two numbers. But we need to figure out their corresponding weights. The weights could be different. Okay, the weights could be different. So we use P to represent their weights. Yeah. All right. Yeah, for the first subcase, we know the probability is P. That means the weight for the first subcase is P. Similarly, the weight for the second subcase is 1 minus P. Then let's do the weighted average this time. We have all the data we need, so we can calculate the weighted average. So let's write the formula. We combine two subcase averages based on their probabilities in this way. Okay, yeah. So the weighted average equals the first average number 1/2 times n plus 1, then multiply its corresponding weight P. That's the first term. The second term, the average number n, multiply its corresponding weight number, that is 1 minus P, its corresponding probability. Then adding together these two terms, so we get our final version of average, weighted average. That's what we need to find for this problem. After we get this formula, that means we solve this whole problem. Okay? Yeah. And from this simple problem, yeah, so you can see the main concept we learned from this question, average case efficiency. That's the main concept. Okay, not just the concept, we also learn how to calculate average case efficiency. Here, using the weighted average to do the calculation. Okay, yeah. Later, when we have many other questions, we also need to calculate the average case efficiency. Basically, we use this idea. Okay, yeah, yeah. The structure could be different, but the underlying understanding is the same from, comparing with this example, the same. Okay, yeah. All right, yeah, so we finish part C. Yeah. Any question? Yeah. All right, yeah. If no question, let me move to part D. Another important question for algorithms. Yeah. Oh, yeah. Yeah, here, dominant. Yeah, actually, regarding the dominant term, this is related to module 2. In module 2, we will look at the, concept, dominant term, and other things. Yeah, here, yeah. So, we do not need to pay too much attention here. Yeah, here, just because, yeah, later, this is the exact version of the formula. But when we use the formula, sometimes we may not use exact version. Sometimes we may use approximate version. Approximate version. Okay, so this we use. This is the dominant term. This dominant term is a good approximate version. Okay, yeah. So we ignore some minor terms. So you can see to use this approximate version, how much we ignored. Okay, the ignored part. Yeah. So the part with M, we keep it. So this part, actually look at the ignored term equals 1/2 P. This term is ignored. Okay, yeah. But we know P is between 0 and 1. P is a probability, right? Yeah. So this number is less than 1/2. So if you ignore this term, we only get a possible error less than or equal to 1/2. That's not much. This small difference, we can take it. Okay, we can take it. So people, most of the time, so this small difference is not significant. Yeah, yeah, but we keep this, dominant term. Yeah. This dominant term we will elaborate in our module 2. Yeah. All right. Now, part D, optimality of algorithms. Another important concept, optimality. Okay. So D.1, minimum selection problem. So we learn another basic question type, selection problem type. Yeah. So let me describe the selection. Yeah. Actually, the minimum problem, everyone knows the minimum problem. Yeah. But actually, it's a special case of the selection problem. So later we will study the general selection problem. Yeah. Here, our problem number 4, find the minimum of an array. How easy it is, find the minimum. Right? Everybody knows how to find the minimum. Given an array, tell me which element contains the minimum value of the whole array. Is it easy to solve this problem? Yes, very easy, straightforward, but there is a very important concept here, optimality concept. The solution is easy, but the concept is very important. So I want to talk about, I want to use this example, this question, to explain the optimality concept. Okay, all right, so let's solve this problem first. Then we have optimality discussion. Now, given an array, here the array, if we do not mention ordered or unordered, then we assume it is unordered. Because we do not mention. We do not mention, you can only assume it is unordered. Okay, you cannot assume it's ordered. Yeah. Otherwise, find the minimum is too easy, right? If the array is ordered, the first element is the minimum. Too easy, right? Yeah. So you cannot assume that. Okay. Yeah. Then, question. Find the index I such that A of I is the minimum of the array. Okay, the question. Yeah, very simple. And the solution also simple. Okay, but we need to do, some very abstract discussion. The discussion is quite abstract. Yeah. The problem type here, selection problem. Selection. Okay, yeah. So what is a selection problem? Here, let me give you the definition of selection problem. Find the kth smallest element. The k should be given at the beginning. Yeah. K is a fixed number. It is given at the beginning. So then you find the kth smallest element in a given array. When k equals 1, that's this minimum problem. Okay, k equals 1. When k equals n, that's the maximum of the array, right? When k equals 2, then you'll find the second smallest element in the array, and so on. Okay, yeah. But there is also a special case, very important. When k equals floor function of n over 2, then this function, you find the median. Finding the median, okay? That's another important selection problem, finding the median. Okay, yeah. So here I give you the reference in the textbook. Yeah, these two sections, 2.3 and 4.5. Yeah. All right. Work and analysis. Yeah. First, let's get a solution first. Yeah. So simple, yeah, but we need to go through the whole solution. Do initialization. When we start, we need a variable called a min. We use this variable to store the minimum value of the whole array. But at the beginning, we assign the first value, we assign the value of the first array element, A of 0, to this variable, min variable. Okay. Yeah, so that's the initialization step. Then, the general step, we need to update this variable when we go through all the elements in this array. So the general step, we compare min with the current element of the array, A of I. When we do comparison, we have these cases. The first, when min is greater than a of I, that means we should update this min value because we find a smaller array element, right? So we should replace this min variable, the value of this min variable by a of I. Okay, so we do a new assignment. Min equals a of I. Okay, yeah. Otherwise, if the min less than or equal to a of I, we do not update it. We do not need to update it, yeah, because we do not find a smaller array element, so we do not update it. Yeah. And we keep doing this iteration until we reach the end. Yeah. So otherwise case, we need to, for the otherwise case, then we need to move to the next iteration. Okay, until we compare with the last element, I equals n minus 1. That means we need to go through all the elements in the array. Not like our search algorithm, when we find a match, we get out of the loop immediately. Here, we do not. We have to go through all the elements from the beginning to the end. Then we can say, if our main variable contains the global minimum value, global, the whole array, global minimum value, okay? Yeah. So that's the solution. That's the solution, all right? Yeah. Yeah. So at the end, our function returns this min value. Then we complete the solution. Okay, we complete the solution. Okay, yeah, it's simple. Yeah. But the question, next question. How many comparisons do we need to find the minimum? So given an array with n elements, how many comparisons? Yeah. After you see the solution here, can you find the exact number of comparisons to find the minimum? It's a simple answer. Can any of you type that number? And I want to see if it's correct. Jeanette, type N. Jeanette, type N. Any Dakota also N. Any different number I want to see? Any different number other than N? Other than N, is there some reasonable choice different from N? Yeah, we need to look at all the elements. Yeah, here, let me give you a little more information. Here, number of comparisons, okay? We only count the number of comparisons, not assignments. You know assignments, right? For example, this first initialization, this is assignment, not comparison. This is not a comparison. Okay, so for the first array element, we didn't do comparison. We just assign a of 0 to our min variable. After that, we do not need to compare min with the a of 0. The next time we only need to compare min with a of 1 and so on. Now, Jeanette got the correct answer, n minus 1 comparisons. Yeah, but not assignments, right? Assignments, comparisons, they are two different operations. there are two different operations. Yeah, here we like to count the number of comparisons. Yeah, because we feel the number of comparisons is a better measure than the number of assignments. Yeah. Although you can use the number of assignments to measure its efficiency, but not as good as comparisons. Think about that. Yeah. Yeah. Later, when I have a chance, I will explain why we use number comparisons is better than we use the number of assignments. Okay, yeah. So you can think about it. Yeah, but here, the correct answer, we want to get accurate, exact answer, not approximate. If approximate, your N is a good approximation, right? Only one difference. Yeah. But here, if we like to have exact number, then we need to use this N minus 1. Yeah. This exact number is important because remember our goal for this part D, we want to study optimality issue, right? Optimality, then this N minus 1, we can claim this is an optimal solution. If N, not N minus 1, if N, then you cannot claim it's optimal solution, right? Yeah. So for optimal solution, we like to use the exact number of comparisons. Yeah. So because we have second half of the story, if this solution is optimal or not. Okay. Yeah. So let me go to this optimality issue quickly before the break. Yeah, we have 5 minutes before the break. All right. Answer is N minus 1. Then the question, is it possible to further improve the algorithm? Yeah. Every time when we find an algorithm, we need to think about, is there any room for improvement? Yeah, because we want, in general, we want to have the best solution if the cost is not too high. Yeah. Yeah. Right? Yeah. If we can control the cost, because finding the best solution, you may need to pay a lot of cost. If the cost is too high, we may not like to pay that high cost. Okay? Yeah. Other than that, then, all right, yeah. If the cost of sorting is less than number to be worth it, right? Unfortunately, the cost for the sorting is much higher. Much higher, yeah, yeah, yeah. The much higher here, I can give you, yeah. But your thinking is correct. Yeah, your thinking is correct. Yeah, all right. Here I can give you the cost of sorting n log n. N log n. So that's the reasonable cost for the sorting. This is the cost of sorting. So definitely you don't want to pay this much cost, right? Yeah, yeah. All right. Later, when we learn sorting algorithms, we will find this number, this cost number, why it is n log n. Yeah. Okay. All right. Yeah. Yeah. But good point. Yeah. Good point. Yeah. All right. Yeah. So when we answer this question, is it possible to further improve the algorithm? Usually we have two options. Okay. The first option, improve the algorithm. Yeah. So if the cost is not the issue, so we always try to improve the algorithm the best we can. Yeah. But it's impossible to improve the algorithm forever, right? You have to stop somewhere, right? Nobody can improve certain algorithm forever, right? Yeah. But how do you know at which point you should stop looking at the improvement. Enough is enough, right? You should stop looking for better algorithm. How do you know which point, right? So the second option, if you can convince people that this algorithm is already optimal, then you do not need to look at it anymore because it's already optimal. Your solution is already the best in the world. There is no reason for improvement. Think about that. Yeah. And this solution, this n-1 comparison, this solution, it is optimal. It is the best that people can do for this particular question. Nobody can do better than this one. Nobody can do better than n-1. That means nobody can use n-2 comparisons to find the minimum of an array with n elements. It is optimal. Okay? Yeah. So here, there is this issue. So this solution is optimal. But the question is, how do you know it's optimal? Right? You claim it is optimal, but you need to prove it. You need to convince people, right? Yeah. When you convince people, you need to give the convincing arguments. Otherwise, people won't be convinced. People won't be convinced. Okay? Yeah. All right. Let's take a 15-minute break. After the break at 7 o'clock, then let's look at the convincing arguments for this question. How to make the convincing arguments that this solution is already optimal. Okay? All right, so let's take a break now.